Presenting this talk about quantum chaos, quantum dynamics, using Fermi-Hubbard models. So in this talk, I'll take you through classical quantum chaos, integrable and non-integrable systems, thermalization, and information scramble. So first of all, what is chaos? In classical sense, we say a system is chaotic if it's very sensitive to initial conditions. So let's say double pendulum. If we change the initial conditions by much, the trajectory is exponentially change. In quantum systems, we don't have any classical trajectories. We have eigenstates, energy levels, and operator groups, etc. So we have something called level statistics. Level statistics is defined as the difference between two adjacent energy levels. So for this gives us a very good idea about what integrable and non-integrable systems are. For integrable systems, these level statistics or spacing levels are defined by Poisson statistics. So they are random. There is no repulsion between these data levels, and these just come out as Poisson statistics. Whereas for chaotic systems, these level spacings have repulsion, due to which you can define the Hamiltonian as a random matrix of a Gaussian.
What does repulsion between levels mean?
So repulsion between energy levels, we'll see through some examples later on, but it just means the energy levels are repulsive because there is a compromise for the spacing in between. So they can't be too close to each other. So level repulsion is the hallmark of quantum chaos. And as we can see,
for a real system, you actually get energy levels. It's like mapping to a particle.
Yeah. For real systems, we can't actually go to like discrete energy levels for like, let's say x equal to something or something. We can't do that. This is only for like on a large scale though. We can see like if we have the occupation number, let's say, if we plot the occupation number, we'll probably see the same statistics. So for Poisson integrables are like this and Wigner-Dyson are like this. So what are integrable systems? Integrable systems are defined as systems that have as many conserved quantities of charges as many degrees of freedom. Because of these constraints, the dynamics of the system are very constrained because of these conserved quantities. In non-integrable systems, there are fewer conserved quantities and degrees of freedom. These show chaotic behavior. So we can explain, there is something called ETH, Eigenstate Thermalization Hypothesis, which was given in 1991 by Lioche, which says in a non-integrable chaotic system, we don't actually have to compute every eigenvalue for the energy for each variable. Instead, what we can do is take it to the thermal average. So basically, if we have this, which is our energy eigenbasis, it says that the expectation value of the operator is just the thermal average of it. This leads our system to thermalize to a Gibbs ensemble. Whereas for integrable systems, because all of these eigenstates are labeled with the conserved charges, you can't actually access the whole energy eigenbasis. So our energy eigenbasis is kind of like a corridor which is governed by the initial QI, initial conserved charges. So our expectation value would look something like this. So because of this fact, we cannot thermalize it to a standard Gibbs ensemble. Instead, it thermalizes to something called a generalized Gibbs ensemble. And as you can see from this is just inverse temperature. And here we instead have something that is a Lagrange multiplier, which is fixed by the initial conditions. So the late stage system somehow carries the memory of the initial conserved quantities. So it thermalizes to GG. So if we want to study any thermodynamical quantities, we have to put the system out of equilibrium. To do that, classically we put a thermal bath or something. Here we can do something called a quantum quench. Quantum quench is basically just changing our Hamiltonian certainty by changing some parameter, let it be the interaction parameter or the Hawking parameter. You change at time less than 0, it was h0, at time greater than or equal to 0, it was h1. This basically puts our system out of equilibrium. Then using the Heisenberg picture, we can time evolve the state. Now, in the out of equilibrium system, we have 2 or 3 things that can be used to categorize these things. So entanglement entropy is one of them. Entanglement entropy is defined, let's say I have a system. And I can basically divide it into 2 systems, subsystems. And I take the trace, the partial trace in B. So like my initial wave function was this. I took the partial trace in subsystem B, and I take that as rho A. And then I compute the entropy in as minus of trace of rho A log rho A. So basically your rho A carries the entanglement that is still in subsystem B. So they are entangled in substance. You still have some information. You can't actually, what it says basically is, if you want to find out the information hiding in A, you can't do it without B. So yeah, so also for this, as you can see, the Gibbs ensemble, it basically saturates, but the expectation value. But for GGE, it tries to oscillate because it retains the memory because of the conserved charges. Similar for entanglement entropy, it saturates, but for integrable ones, it tries to oscillate. So as I said, operator growth is also one of the things that we use to study. That is studied by using something called out of time ordered correlator, which is defined as the negative of expectation value of WT V0 commutative to school square. WT is basically an operator that is evolving in time, and V0 is at time equal to 0. So in these systems, these CT or OTOC is proportional to exponential lambda L T at early times. Lambda is the quantum Love exponent, which basically, if it's a positive entity, you get to see that it's actually chaotic. So, as we saw in the entanglement entropy 2, kind of shows that oscillatory graph, integrable oscillatory, so it won't show chaos. So, I have used Hubbard model here, a 1D Hubbard model. It's defined as this is the kinetic term, and this is the on-site interaction term. So if we increase our kinetic term to the point that it overpowers the on-site repulsion, we get a quasi-particle that is called a doublon, where basically two spinful fermions, let's say electrons are in opposite spin, they come together and travel as one instead of having two different electrons. So this can either move as one, or it can decay and go in two different directions.
So it's a spin particle.
No, spinful. So double operator is just the number operator spin up, spin down at site I. So now we are going to take the OTOC operator. This basically says that the doublon at site I will evolve with T, and we are seeing at site J what is the overlapping of it. So let's say at site I have a doublon at time equal to 0. Now I quench it. Let's say I make the interaction parameter go less, so that it hops. So when it hops to J side, at later time I'm going to see the correlation between it. So measuring the spreading of doublons gives us quantum chaos. If it's an exponential growth that we can fit to this thing, quantum Laplace, and we see if the Laplace exponent is positive, we see it's chaotic. So yeah, doublon OTOC comes like this. I didn't take the Laplace exponent. For integrable, it's slow. For chaotic, it scrambles very fast and saturates. This is the light cone spread. So we can also spread the light cone in space and just in time and with the position I. You can take the wavefront of velocity, which is called butterfly velocity. So yeah. So basically like that, if we instead of the doublons, we have it decay into two fermions and going here and here. Again, we'll have basically a subsystem A and a subsystem B. And we can take out the entanglement entropy between the two subsystems. So yeah, okay. Yeah, the two entanglement between two subsystems would look like this for a chaotic one that is our Hubbard model. It will saturate, scramble very fast. For non-integrable ones, it's linearized, saturated straight like that, but integrable slow. So yeah, after this, so what have we learned so far is that in a chaotic system, we have some local operators that had their own eigenvalues or something, but at late time it just thermalizes to a Gibbs ensemble. So all the information that was encoded in these operators is lost into thermal entropy. This sounds oddly familiar to a black hole where we have some correlators, but those correlators are seen to us like thermal radiation. So that is a good way to say, this is not a complete one-to-one mapping of metric or any geometry. There is no holographic tool to it. It's just a diagnostic of the thermodynamics of it, so that we can have an idea that maybe it's fine to use condense matter systems to study black holes. I have not got into black hole physics part here because there is not much time left enough. Yes. So black holes have thermal Hawking radiation where there is information loss. There is something called a page curve where basically just like this we have two subsystems. At the event horizon, we can take two subsystems. One is the interior and the exterior. The exterior could be taken as the radiation and the interior as the work. Where just like the doublon, we had a decay into two spindles fermions in a different direction. We have pair creation here, where one goes into the interior and the other in the exterior. We can calculate the entanglement entropy for this too, and that is the page curve. Because of unitarity, it has to rise and then fall. So MSS, there is something called the MSS bound, which was given by Shankar Sanford, which basically says this bound, this chaotic bound cannot be more than bound by this this value of 2 by kVT by h bar. So because black holes have the most temperature, they are the fastest scramblers we have. So yeah, the OTOC of that would also saturate like this, but at a way faster rate than we have in something like a Hubbard model. So this is the page curve for the entanglement entropy. So why to do this? Because strongly interactive quantum systems can act as black holes, which we are seeing through holographic tools like the SYK model, which I haven't shown here exactly. But we see that the scrambling happens like this only. It's a very saturating thing, very fast thing. So we can have an idea by strongly correlated, but we can't do that in integrable systems obviously. So chaotic strongly correlated integrable systems are the way to study black holes. And yeah. So also one thing I found out in my thing that I didn't show here was that there is two things. There is VE, which is the velocity of the entanglement entropy, and VB, which is the butterfly velocity for this microphone spreading that we saw. So what I found was that VB was greater than VE. That is, the operator was going faster than the entanglement of the entropy could happen. Yeah, so the local perturbation spread across the entire system exponentially fast.